Good afternoon or evening, depending on what time zone you're in, and welcome to AABC's Tab Talk webinar series. My name is Karen Shunk, and I'll be your moderator today. I'd like to go over a few housekeeping notes before we get started. We encourage you to submit questions at any time using the Q&A button at the bottom of the screen. We'll be holding a Q&A session at the end of the presentation, but please don't hesitate to submit questions as they come up. The chat function is where you can make general comments and chat with attendees. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform panelists, and our technical assistants, our technical experts will assist you. Finally, this course has been approved for 1 hour of continuing education credit. After the webinar, you will receive an automated email with your proof of attendance. Here's a little bit about our speaker today. Scott Mahanes is a dedicated tab professional with over 16 years of experience in the field of testing, adjusting, and balancing. He was an operations manager for a small office for 4 years and a certified TBE for over 3 years. Over the last 2 years, he has been with the University of Virginia, where he has transitioned into the world of HVAC operations and controls. His expertise in this field allows him to ensure optimal performance and efficiency in HVAC systems. So without further ado, I'm going to hand it off to Scott to kick off the session.
All right, thank you, Karen, for that introduction. I think I've messed something up here. Give me 1 second. And that is not true. Let's try this again. Ooh. Sorry about this. All right, so I'm going to this other.
Scott, I would suggest that you try sharing the screen again, but with just with the presentation, maybe.
Okay, yes, I think I have it now. Sorry about that. Nothing goes to plan, does it? So yes, Karen, thank you for the introduction. We're going to talk about mass airflow and this mass airflow triangle. I'm really excited to share this information about the subject matter that's kind of really not typically talked about much in the industry. We usually talk about volumetric flow rate a lot. We focus on that, but there's really another perspective that needs to be understood, and that is the mass airflow perspective. You'll hear me say that a lot. And there's some definition that needs to be given to the term CFM. Sometimes we just say CFM this or CFM that. A lot of times we're referring to volumetric CFM, but there is a difference between ACFM, SCFM, and then I've kind of created another CFM type called MCFM, which I'll go over. And really, when we have this confusion about what type of CFM we're really talking about, we can kind of make mistakes because we're not really all on the same page. Sometimes it's from the design team even that's not exactly a specific enough number to understand what the intent is. And so hopefully you read the abstract that I had where it talks about how mass airflow is more important than volumetric flow rate, but yet we kind of just focus on volume alone. What's interesting is everything we hold near and dear to HVAC operations, like ventilation rates, building pressurization, heat transfer, really is related more to mass airflow than it is to volume. So we're going to talk about those differences. Density oftentimes is sort of overlooked. We don't think that it really impacts us all that often. And so I'm going to show you that even if you do your correction factors 100% right and you have a 100% accurate volumetric flow rate, the use of that volume that you have, the way you allocate it, can lead to some significant errors. above 10%. So we'll show you that as well. And then really what the rub is that if you understand that airflow isn't just volumetric flow rate alone, but it's also related to the mass and density, that relationship that's there, you can get a more precise way of testing, adjusting, and balancing, and a more precise way of controlling airflow. So we'll talk about that as well. So I have 4 learning objectives. One is to just discuss some terminology just to get a baseline starting point. And then we'll talk about this mass flow triangle and what it really means and what it looks like. And then once we've discussed that, I'm going to move into some examples as to really how does this actually impact the way it is we do testing, adjusting, and balancing, or the way it is we report it, and even designing it. We're talking about maybe getting a little bit better specificity on the actual targeted value that we need. But even if that is done all correctly, there's an issue that we have. If I have a calibrated airflow sensor that's perfectly calibrated for volume, I still have an issue with the way I control airflow, and I've got to talk about how there needs to be a shift or a paradigm shift to controlling airflow, not just by volume alone, but by mass. And at the end of this, hopefully I have time to share with you a simulation that I have that shows you how mass airflow numbers don't equal the way you set up air handlers to run. And oftentimes you end up with a large error, up to even 125%, I think I'll show you in this example. So starting off with defining some terminology, what is NVD? Most of us think that NVD is a manual volume damper, typical acronym for most of our mechanical drawing sets. And that is true, but I also want you to consider, and I'm piggybacking off this, NVD can stand for mass, volume, and density. And it's something that you want to be familiar with. Mass airflow is a very new concept to us. We don't really talk about it that often. And so really what mass airflow is, to define it, is it's the weight of the amount of molecules that are going, passing by a single cross-sectional plane over a length of time. Okay. Similar to volume, because volume is the amount of volume going through that cross-sectional plane over length of time. But for us, in minutes is our time, and our weight is in pounds. So we're talking about the amount of pounds of air we're moving per minute as our standard unit here. And when you see me refer to this in the future of this presentation, I'll be referring to it typically as the capital M value. Volumetric flow rate is also kind of not known to, no, I'm just kidding. We know volumetric flow rate very well. If you're a tab professional, you should know this very well. It's your CFM value. All right. So I don't think I have to discuss what that really is, but I'm going to refer to it as the V, volume value, as an abbreviation. And then density is the mass of air per unit of volume. For us, it's in pounds per cubic foot. Okay. And it'll be abbreviated by D. So here's a new way of thinking about NVD. It's mass, volume, and density. Okay. I have a pretty interesting illustration that shows you the difference between mass and volume. It's rather interesting. If you had a container that had 1 cubic foot of air trapped inside of it, the mass of that air, and this happens to be basically at standard density conditions, the mass of that air could be 0.748 pounds, 0.75 pounds. If I add pressure to this container and I increase that pressure and reduce the volume by half, the volume's changed by half, but what doesn't change at all is the mass. In fact, if you count the amount of particles that are in the left container and the amount that are on the right, the only difference isn't the count, but the spacing between them. And so there's effectively no change to the mass in the containers, but yet the volume is. And so what we see is temperature, pressure, relative humidity changes. When they change, the mass and mass flow rate of the substance will remain constant, but with volume, the volume has to change as the density changes. And so that's the basis of understanding about mass versus volume. And there's a good reason why mass doesn't change. So now we can talk about this triangle that exists, and this is nothing new. I didn't create this, but this has been used in scientific fields for a long time. But it's a pretty good depiction of how mass, density, and volume are all related. and really the math of what you have to do to get from one value to another, basically, or a couple values to the other. And what's interesting is mass is on top. It's really, king of the hill, top of the pyramid. It's the dominant value. Mass is, not volume. In fact, volume doesn't dictate anything. Mass does. And the triangle shows you that if you know the mass value and you divide it by, let's say, a known density value, you can get to the volumetric flow rate. If you know mass divided by volume, you can get to density. If you know density and volume, multiply the two together and you get the mass flow. I'm going to bookmark that to the corner. And I'm not sure if I'm hiding this or not. And then we'll talk about some of these airflow rates that I said earlier: ACFM, standard CFM, and measured CFM. ACFM, actual airflow, air CFM, this is the actual volumetric airflow rate. This is nothing different from the CFM value we typically talk about all the time. It's just to be more specific about what you're talking about. If you call it ACFM, you're really talking about the volumetric flow rate alone. And this value is really synonymous with the V value in the triangle. Okay. But what's interesting about this value is it's tied directly to the density. And oftentimes we don't report the density value at the time we report a volumetric flow rate, but the density does have its place with volume at the time that you measure the volume. We just tend to not report that value. So they are interconnected and they're sort of married together in relationship, which I'll show you later in this presentation about how that really works. Moving on to standard CFM, this is kind of uncommon to us. It's the SCFM value. And really what it stands for, it's the mass airflow CFM equivalent. What's interesting about mass is it's in pounds per minute. We said that earlier. And pounds per minute, we don't have meters that measure that. We don't have scheduled values. Imagine if you had 7.5 pounds per minute shown on a drawing that was next to a grill. Set the grill to 7.5 pounds per minute. None of us would know how to do that. That's not a common thing. By the way, 7.5 pounds is like 100 CFM at 70 degrees, and barometric pressure of 29.92. So there's a way to get to the CFM value by referring to the mass. And so simply what we do with the mass number is we divide it by standard density and we convert it into a CFM equivalent number. So the mass flow of SCFM value is simply the airflow you're going to have in volume if you were at that standard density condition at 0.75 pounds per cubic foot. And really this value is synonymous with the M on this triangle. The third type that I want to talk about briefly, I don't want to spend a lot on this, is the MCFM or DCFM value, digital or displayed or measured CFM value. And this, what I'm talking about with this is our instrumentations, our tools that we use are very different. We have rotating vane anemometers, we have digital micromanometers, we have hot wire anemometers, and sometimes our tools don't do full compensation. If I have a DMM that doesn't have a temperature probe with it, it's going to do a barometric pressure auto correction, but it doesn't do it for temperature. And so as a test and balance, professional, I have to be sure that if I'm using a DMM without a temperature probe and I'm measuring something other than 70 degrees, I need to compensate for that measurement. And the displayed value that's on that meter doesn't always mean that's exactly what I have there, because if the temperature is different, then I definitely have to correct for that. And so oftentimes our displayed values on our tools are not exactly an accurate measurement because we have to consider the density at the time we do that test. And what ends up happening is this value comes in somewhere in between the ACFM and SCFM value. Why? Because it's partially compensated and not fully compensated. And in the end of the day, it ends up being synonymous with nothing on the triangle. It's kind of a bogus sort of number. There's a good analogy I came up with that shows you the difference between actual standard and measured CFM. And imagine you went to Amazon and you ordered 1 cubic foot of air. I know that's not common. Like, who would ever do that? Air's free. But if I ordered 1 cubic foot of air, I'm going to get the same size box, 1 cubic foot box shipped to me. And that's a guarantee. There's nothing going to change with that. It's always the same size box. That's what I'm ordering. But what I don't get guaranteed is the amount of mass of that air. It could be standard, it could be a little bit higher, it could be lower. I'm not asking for the mass. I'm only asking for the volume in the case of ACFM. When it comes to ordering 1 cubic foot of air under SCFM terms, though, the box is open because there's no surprise. It's the same size box, same volume, but also it's the same mass. So as you can see by this example alone, ACFM or volumetric flow rate by itself is not specific enough as a targeted value, whereas mass is, standard CFM is, because we know both the volume and the mass combined. Measured CFM, this is kind of funny, comes in a little bit damaged. We don't really know what we have here when we have an uncorrected value that's just the displayed measurement being done. That's not always the case. Sometimes you are close enough or right at standard density conditions, or you don't need to worry about changing for temperature. But this is what it kind of ends up being. And you have a question about whether the volume is correct or even the mass. You can reverse this and say, well, what if I ordered 0.75 pounds of air, the mass of air from Amazon? When it comes to my doorstep, it's going to come in different size packages. There's no guarantee of the volume that it's going to come in. And so it could be standard at 1 cubic foot. It could be a little bit larger. It could be smaller. And then with standard CFM, the difference is there's no surprise. I know it's always going to be the same size box every time. Measured CFM, again, comes in damaged if it's not corrected for correctly. And oftentimes, I liken it to being like ordering from wish.com or temu.com. Kind of becomes like a questionable product. So here's that triangle, and I'm going to share an example with you on a 10,000 CFM RTU, constant volume RTU. The math is simple. You take the actual air density, multiply it by the volume, you get the mass. And I realized when I started thinking through this mass flow situation that there's another side to the triangle, another dimension you could talk about, which would be a different density side. Now, we said that mass doesn't care about density. It's the same value no matter what. So if mass is 644 pounds on the actual density side, I can move it to a standard density side of the triangle at 644 pounds. Divide that then by standard density, and you get a standard CFM value of 8610. Now, that's very different from 10,000 CFM, but what's really going on here? Well, I kind of turned this into a tetrahedral now with a third dimension on the third side, and the measured side of airflow now shows you what's really going to happen as a technician if I go out onto the field and I go to measure for 10,000 CFM. Now, the goal is I have a 10,000 CFM design unit. I need to set the fan speed to 10,000 CFM. So as a technician, I go out there and I measure this 9518 CFM without a temperature probe on my DMM. And I need to compensate for the temperature, which happens to be 125 degrees. It's reheating to 125 degrees, let's say. By the way, this would be like 1,500 feet above sea level. And so if I have 125 degree temperature, I need to turn it into an absolute value at 585. Divide it by standard absolute of 530 and get a factor of 1.1038. When I have that factor, I need to square root it in order to get a correction factor for the velocity or volume. And so this is really nothing new. This is by the book of correcting for temperature from my measured value that doesn't correct for temperatures. It's considering 70 degrees standard temperature. And so what's interesting about this case is I've accurately measured 10,000 CFM now. Okay. And I would normally, as a technician, sort of stop there and say, okay, well, the design's 10,000, I'm measuring 10,000, and then my day is done. It's amps, volts, RPM, static pressure, closeout time. Because I have the targeted value that the design intent seemed to show. What I'm going to show you is this sort of paradigm shift of understanding that measuring volume accurately isn't always just good enough. You have to allocate what you measure correctly. And the only way for me to allocate what I measure here in this situation to what's really being moved by the fan is to actually turn it into a standard CFM value. Now, to do that, I need to get the right density value. And initially I said, well, you could adjust the presumed density, but no one knows that. No one's measuring that. Or you could just straight up calculate density. And you know what's interesting about this is the only other piece of information I need to know is barometric pressure to get the density value calculated. So if I know the pressure is 28.44, you take that divided by 585, multiply by 1.325, and now I have a density of the air density at the same time I have the volume. And you can see on the triangle below in green, I have the density value of 0.0644, and I have the CFM value of 10,000. And once you have those two values, it's simple math. You multiply the two together, you get 644 pounds per minute. You can transfer that over to the standard density side, divide it by standard density. You can divide it by standard density, and then you get that SCFM value. And so what's interesting here is I'm really not moving 10,000 CFM at the fan inlet. I'm moving 8610 CFM at the fan inlet. In fact, if I were to measure this duct traverse when I was at like standard density conditions, which I think is below 70 degrees, but if I was reading this at a lower temperature, I'm going to see that I'm actually moving closer to the 8610 CFM. The problem is the allocation of where I measure the flow rate. I can't measure 10,000 CFM at a different density and allocate that measurement to what the fan's moving. That's not going to be right. Now, the triangle tool kind of helps you go reverse, convert from SCFM back to ACFM. So if I know that I need 10,000 CFM from the fan, and let's just presume this is that standard density requirement, then I can take the 10,000, go reverse, multiply it by standard density, and get the mass flow target that I need. Transfer that mass flow to the actual density side, divide it by the actual density, and then I get a new targeted volumetric flow rate I need to be at to be equivalent to 10,000 standard CFM. I know this kind of gets complicated, but this is the conversion that's required to go from volumetric flow rate to mass flow rate and back. And simply, this is a decent tool that can kind of help you do that. At least shows you the process. Let me show you some examples of what happens in the real world with like a VAV. So if I do a pitot tube traverse on the inlet of this box, if I don't use a temperature probe, my measurement's going to come out to 2038 CFM, let's just say. But then I need to consider that the density is different from standard, and this is at sea level. So at 0.77 pounds per cubic foot, I need to do a correction factor for the temperature of 50 degrees. That ends up becoming a 1999 value. And so now this looks good. If the sensor believes it's doing 1999 and I'm measuring 1999 volume, we believe that this is a very good calibrated airflow sensor. But I want to show you that with a mass flow perspective, there's actually more going on than what you realize. Because if I take the volume, multiply it by the density, I get this mass flow number. If I divide that by standard density, I actually get a standard CFM value of 2077. Now, I don't want to complicate things, but the reality is what I'm trying to show is there are 3 distinct different values of airflow on this example right here. There's the measured flow rate, which is partially compensated and not fully correct. There's the fully corrected compensated airflow reading of 1999. And yet there's also an airflow rate of 2077. And it kind of gets confusing, but that's what really exists at all times. We just didn't realize the SCFM value was there. What's also interesting about this example is I could use a different method of measurement, and I could use a flow hood on the discharge side, assuming it has no leakage. And I should come up with the same values, right? I should measure 2038 on the meter with no temperature probe compensation. If I compensate it, I get 1999. And then if I go to a mass flow conversion, it's 2077. And what's interesting about this example is we believe oftentimes this adage, I'm going to change this to a different scenario. There's this adage we believe in that's called what goes in must come out and what goes out must come in. And we believe that if we measure 1,000 CFM over here, again, presuming there's no leakage or additional airflow source, that 1,000 CFM is equatable or can be allocated to every section of this air handler. And so we might measure 1,000 CFM in volume here and say, well, there's a flow station right here, and I can actually calibrate it with this measurement. And so we'll calibrate the flow station with 1,000 CFM. And we believe in this adage that I can do that because of what goes in must come out. Well, I learned a year ago that this is really called the law of conservation, and we're utilizing the continuity equation to sort of do this. And reality, law of conservation has nothing to do with volume and everything to do with mass. And so I'm going to change these numbers slightly, which shows you that if you have a standard CFM value measured over here on this side, it is the same across the board. Mass flow is the same, but if you look in red in the volumetric flow rates, that's very different. At every stage, every different density airstream, it's a different volume. It's crazy. Now, what's really happening here? Well, mass dictates what's really happening, mass flow. And so that's a fixed number, and really density and volume balance on top of mass. And so as density goes down, it's a seesaw reaction, volume goes up by the same proportion, inverse proportion. And as density goes up, volume goes down. Density and volume are married together in a relationship that's inseparable. And so what's interesting is if you see with these numbers put in here, that if you're at standard density conditions and your level on the left here, you can see that the 1,000 CFM of volume is the same as the mass flow. But if I reduce the amount of density, I've increased my volume, and the standard CFM has not changed. And inverse of that is if I increase density, the volume has to go down. So what's really happening in this case is at 0 degree air, I'm much higher in density. And so my volume goes down to 868. And when I preheat that to 70 degrees, I level off at 1,000 CFM matching mass flow. And then if I subcool it down to 50, I increase density, I decrease volume to 962. And then when I reheat to 120, the density goes down again, the volume goes up. And it's just like a seesaw relationship. And so what's interesting is I cannot measure volume on this side and allocate that measurement anywhere else where there's a density change. And believe me, I've done this hundreds of times in my career. It took me 2 weeks of lamenting when I realized I was actually incorrectly allocating the CFM value. And it's not that I'm measuring volume incorrectly. It's that I allocate it incorrectly. And so that's one of the strange things about mass flow, that if you see it from that perspective, you can actually understand what's really happening. So going back to this VAV, if I happen to have an open reheat coil and I go to 120 degree discharge, well, my density's changed. But what doesn't change is mass. We've talked about how that's a law, that it stays conserved. So if mass stays the same and density goes down, the volume goes up. And if you want to go do this test, you take a calibrated airflow sensor at 50 degrees and you're perfectly calibrated, increase the discharge air temp to 120 degrees, and you will see a distinct difference between what you measure and what the airflow sensor shows, not because the calibration gets wonky, it's because the volume has to go up because the density's gone down. And if I were to calibrate this sensor based on what I measured on the discharge side of this box at this condition, I would be miscalibrating this VAV flow sensor by, I think it's 13 or 14%. So it would be a big error to have. Now, what's interesting about the two sides is there's one number that's consistent, and that's the SCFM value. It's 2077 on both sides. So if I convert to SCFM, I can actually see what's really happening. And I can see that they're both equal on both sides. Another thing where this kind of becomes an issue is room pressurization. We believe that room pressurization is a volumetric flow rate difference controlled by volume difference. And on the left, you'll see that I have a positive 100 CFM differential, and on the right, a negative 100 CFM differential. And you would think that respective to a neutral space, you would have a positive pressured room on the left and a negative pressure room on the right. However, if you look at it from a mass flow perspective, which really drives the room pressure under these conditions, which would be like 3,000 feet above sea level at these temperatures, you'll see that I have a very different CFM value, and the differential of those values actually goes really, really far off. Now, this is an extreme example, but 100 CFM volumetric difference is very different from a minus 160 mass flow difference. And a minus 100 CFM volumetric flow difference is very different from 71 positive difference. And in reality, these rooms are going to drive into different pressurizations, not because there's something wrong with calibration of the volume. It's because the volume alone isn't the right value to differentiate what kind of pressure you're going to have. It's on mass. And I promise you, if it's true for a room pressure, the same thing's going to happen with a building pressure differential. Okay. And another kind of example of where this goes wrong is I might not be able to measure the outside airflow station correctly right here. And so I'll turn the unit into 100% econ mode. And if I'm smart, I'm going to actually neutralize this pressure right behind the mixed air damper, the return damper, so that I minimize any leakage from the return air system to this. And when I do this, I expect to have the same amount of airflow on the supply side as I do as the outside air, because it's all outside air sourced. And so if I have a calibrated flow station, or if I do a measurement of airflow on the discharge side of this unit at 10,000 CFM, can I calibrate the outside airflow station to the same value I see on the supply? Oftentimes I used to do this. But what if I told you the outside air needs to be 10,980, not 10,000? And these are the conditions you need to be at to get those values. And what's interesting is in volume, I can't compare the two. I can't allocate what's measured on the supply side to what's on the outside air because they're two different densities. I'm at 100 degrees on the outside air temp, 50 degrees on the discharge of the supply. But if I converted to the SCFM values you see, which is 10,392, I can compare the two. So one of the things we got to understand is when we do comparisons of airflow stations, when they're in different densities, you can't do it volume to volume. The only comparison you can make is mass to mass. So SCFM to SCFM is the only way it works out. Now, if I calibrated this outside airflow station to 10,000 CFM, that would be a 9.8% mistake. So you've got to be careful about how you allocate what you measure. We also do comparative tests with supply, return, and outside air, often like an ABC sort of test. And so if A is the supply, B is the outside air, and C is the return, and I expect to have no relief because the relief damper is closed, then we think that A, 10,000 minus B of 3,000 should yield a result of 7,000 on C. And in fact, it shows that right now. And normally we would say this looks good. But you have to do it from a mass flow perspective and not volume. And if you convert these into what they really are in mass, the ABC comparison is very different. A minus B equals 75.53 at C, and C is not at 75.53, it's at 69.35. And so you have an 8% error. Okay. In summary, we really have, when setting airflow different density air measurements, it's going to cause an improper balance and or calibration. And we've seen this with the VAV example, with our comparative airflow station example, and with constant volume fan setup. Room and building pressurization is dominated by mass flow, not by volume. Indoor air quality or minimum ventilation standards, ASHRAE 62.1 table of minimum ventilation rates, they are mass flow numbers. They are not volume. And so it's the mass flow number that is important to control to. Coil performance, we didn't talk about this, but coil performance or BTUH transfer is dominated by mass flow. Doesn't really care about volume. In fact, your 1.08 times CFM times delta T is kind of predicated on having a consistent standard density. If the density is different, the value is different. Moving on quickly, let's see, how much time do I have? No time. Oh, I got some time. Okay. I want to go through simulation real quick on airflow control, because you can get the calibration on the flow sensors perfect, but the control of that airflow is still going to cause a little bit of a problem. And so for that, I'm going to go to this simulation. And what I've done is I've been able to track the air density of each of the supply air, return air, and outside air flow rates. And I can actually set these targeted values. And what you need to focus on is that the actual outside air, exhaust air, and building performance, there's going to be a targeted value we're trying to achieve. And then there's an actual value we're going to end up having and an error we're going to end up having based on the actual differences that occur. And so in green, you can see my volumetric ACFM values. Traditionally, we think that if we're pushing or moving to 25,000 CFM, that if we subtract the outside air flow station set point or airflow, we should be tracking the return fan to that difference. So 25,000 minus 5,000 is 20,000. And in green, this table sort of looks, that's what it looks like. It looks like you're tracking this correctly. The problem with this is if you convert these values into the mass flow standard CFM values, the math doesn't work out like you think it does. And in reality, what we do in standard CFM at those points yields a result of, in this case, an excess of 980 CFM of outside air. So I have almost 20% more outside air than I want to have just because it's a mass flow imbalance. So volume alone cannot control my system correctly. It needs to be done under mass. In fact, I have this neat button that shows you the comparison to standard. If it'll go to it. Yeah. And if you go to the standard CFM value control, we actually hit the targets 100% of the time. It's never an issue of not getting the result that you really want to control when you're controlling by mass. But when you're controlling by volume, the volume is going to be very different. The math's not going to work out. There's a lot of things that you could talk about with this. There's some caveats to how air handler systems might change. You could have a closed relief damper and not have it open. The results are going to change slightly, but ultimately we have an issue related to the way we control airflow because volume can't do it correctly. And when you look at it from a mass flow conversion, you have to control it by mass flow. There's two problems that occur when we aren't controlling this correctly. There's more than that. Actually, let me summarize that for you. Go back to it. Really, the benefits that occur when we do mass flow control versus volume kind of changes between seasons. Basically, in the winter time, we achieve less operational costs because we're bringing in less outside air than we normally would. That also helps us with our mixed air temperature. We have a higher mixed air temperature when we're bringing in less OA of colder air. And so we have a little bit of savings when it comes to that. We also kind of delay the freeze trips or the coil protection that's necessary because we're bringing in a higher mixed air temp. We also usually get a less positive building pressure. And honestly, in the wintertime, colder days outside, we actually benefit from a neutral to slightly negative building. It's in the summertime when you really want a positive building. And so you get a lot of benefits in the wintertime. And then the return fan tracking becomes an issue when you don't have the right control point of, like, let's say 5,000 CFM differential. And that's really a brake horsepower issue for the supply fan being overworking. And it's a lot more wear and tear on the supply fan side versus the return. In the summertime, you get a lot of the same benefits. There's some caveats or changes to that can occur. But ultimately, that's kind of where we're at. This paradigm shift of going to mass flow control gives us perfect control over the air handler system, but it's not always the case when we're trying to do it with volume. In fact, the only time volume is going to work is if you have 70-degree outside air, 70-degree return, 70-degree supply air. And that's never going to happen. And so hopefully you can kind of use this information to sort of look at how you allocate your CFM. And then you can also look into, for the future, I mean, this wouldn't be for tab professionals, but can look out for control strategies that are going to utilize mass airflow control versus volume. Okay. That's all I have for you right now. We'll open up for Q&A.
Thanks, Scott. We do have a few questions queued up. And this first question has an abbreviation and acronym in it, so it might be good to remind the audience what that acronym means. The question is, it seems like when a VAV goes into reheat mode that it increases the volume of airflow to the space. How does this not change the room pressurization?
Yeah, so the room pressurization, like I mentioned earlier, is the difference in volume doesn't dictate how the room pressure is going to occur, because it's not counting for what kind of mass, volume, or molecules there are. And so the mass airflow differential is what dictates the pressurization of the room. And so that's kind of a new concept. We haven't really talked about that before, where volume is usually tracked. The difference of mass needs to be tracked to do it properly.
Okay. Let's see, next question. What would it take to achieve mass airflow measurements from an existing volumetric airflow station?
Yeah, so existing volumetric airflow stations really need density information to calculate a standard CFM value. And so most of our airstreams have temperature sensors already in them. And the only new component you probably need to add in beyond doing the logic changes would be to add a barometric pressure reading. Now you can get that from a weather station centralized to your location, and that's going to do just fine. You have to understand, though, that the weather stations standardize the pressure at the location you're at. So it's very interesting. In Charlottesville, we're 600 feet above sea level, and our barometric pressure baseline is 29.92 inches, as if we were sea level. You can go to Colorado, and it's the same thing. Your baseline barometric pressure is standardized as if it were sea level to 29.92. So you need to make sure that the barometric pressure you use from a weather station readout gets unstandardized to your location. But otherwise, that's all you need. You just need a barometric pressure sensor reading to bring in and calculate the temperature, barometric pressure to get to your density, and then multiply your volume and density together to get to the mass, and then divide mass by standard density to get to a standard CFM value. But the conversion is not that hard. It's very easy to do, just with a temperature sensor and a barometric pressure sensor added to the airflow. I know that's probably a long answer, but that's what it would be.
Okay. We've got another question. This is a question from John Dettinger. John, I hope I got your name right. Why would there be a benefit to having negative building pressure in the winter?
So in some cases, the warmer, moist air in the wintertime is in the building, and you would be protecting your building envelope better with a neutral And I'm not saying you want to have a negative building, but a neutral to slightly negative pressure. If you're positive in pressure in that state, you're actually pushing the warmer, moist air through the envelope outside. And that's not always a great thing for the building envelope.
So we've got another question. How much does, well, this kind of sounds like it relates to the most recent question. How much does relative humidity impact density changes and airflow calculations?
Yeah, that's a good question. The relative humidity is a minor change when it's like 105 degrees or less, I believe is less than 1% accuracy error. So until you start measuring airflow like up in the 115, 120 degree mark, you're really not going to see relative humidity impact the accuracy of the airflow calculation. So relative humidity is just a minor impact to most of our HVAC applications. Okay, so we would love to get some more questions from the audience. We've gotten some good ones so far. So go ahead and put those into the Q&A window rather than the chat. So, you know, when I was looking at your bio, Scott, I noticed that, you know, you moved over the last few years to the University of Virginia. And I'm just wondering, you know, what were the changes that you needed to make in terms of, you know, how you managed the HVAC, you know, or how that, you know, how you were able to update your skills and, you know, what kinds of changes you saw there? Yeah, that's a good question. When I was a tab professional, there's a lot of focus on getting jobs done. It's very different when you go to an owner and operator role. And so I was able to ask a lot of questions I didn't have the ability to even ask when I wasn't looking at it from an owner operator's perspective. I also had the benefit of having some leisure to really go through a lot of data and testing and research. And so a lot of what I've sort of discovered or figured out, which I shared with you in this presentation, is related to just being able to ask more questions, more in-depth questions. And I, you know, as an owner and operator, you have to focus on a lot more. I don't just have to make sure that I'm saving energy, because that is a good thing to do. I need efficiency, but I need that for more than what you realize. I need to actually provide the comfort and control to my occupants in my building at all times. And the benefit of being efficient with your equipment is you can guarantee that for a longer period of time to satisfy your occupants, because I have to check the box on all of those things. I've got to make sure I save energy, but I also satisfy what's needed in the space. And the longevity and the life cycle cost of the equipment also comes into play. So there's a lot of factors that come into thinking about operations that I've never had to consider before. So yeah, it's been interesting. Cool. Okay, so we have another couple of questions that came in from Stanley Barge. Are you able to provide those barometric to density calculations? Yes, I can. And I guess I can email that. Yeah, it's a standard conversion. Like for every, I guess what he's asking, for every like 100 feet of altitude change, we end up with a 0.1 inch mercury change to density. So if I'm 5,000 feet above sea level, the simple conversion, the quick simple conversion is to say, well, 5,000 divided by 100 times 0.1 is a 0.5 difference from 29.92. So 5,000 feet above sea level turns a barometric pressure from 29.92 to 24.92, which is in the ballpark. But yeah, I can provide more for that. Great, thank you. Yep. Another question from Stephen Smith. Are you working with companies manufacturing airflow measuring stations to include the temp and barometric logic, especially in critical environments like labs with critical space pressures? I think that would be relevant to your current situation. Yeah, so there are some airflow stations that are already doing that. I'm not working with anyone right now. You can get temperature and barometric pressure compensated for already with some airflow stations. Not all, and certainly like there's a lot to do to get there. But no, I haven't actually worked with anyone on that.
Mm-hmm. So I just wanted to go back to your experience, moving from a small office to UVA. I'm just wondering, how was that in terms of scope? How was that as a change? Because it seems like, UVA would be sort of a 247 kind of environment and, much larger. And I just, maybe you'd say a few words about that. We'll get back to some of the audience questions.
Yeah, so UVA has roughly 500 buildings that have DD, like some sort of control system. And HVAC, controls are we're plentiful with what needs to be done, and then there's constant renovation and even expansion that's occurring. So the scope of the work that I can be involved in kind of varies, but it's very specific to HVAC operations for us, and I do get to dabble in control systems quite more than I used to with being a TAP professional alone. So that's one of the things that I've had to do is learn a lot about control logic and strategies and typical standards for control systems. And so that's the group that I work with is automation services with our facilities management group at UVA, and we're continuously expanding, and there's a lot that needs to be done, and they're very good at everything related to controls. So I've had an interesting opportunity to come in and really use my experience as a TAB professional to sort of bracket and bookmark, I guess you could say, bracket around what they do well with controls and give them a better insight on efficiencies related to the HVAC equipment, and help with that.
Sounds like never a dull moment. Well, we do have a couple more questions. So thanks everybody. Anybody else has any more questions, get them in now because we're pretty close to the end here. We have one from an anonymous attendee. What instrument did you use to measure barometric pressure specifically? Not ballpark, as buildings in LA could be above sea level. Not sure what LA is. Maybe I don't know if that's actually Los Angeles. So what instrument did you use to measure barometric pressure specifically?
Yeah, so your digital micromanometers are barometric pressure sensors. If you take a look at your absolute pressure mode, when you just take a simple measurement with no tubing on, you'll get a barometric pressure reading. And that's one of the interesting things is we often sort of don't know that value because we don't have to. The meter's automatically compensating for that. So pretty much any one of your digital micromanometers from, Short Ridge, Evergreen, Telemetry, TSI, they're going to give you an absolute pressure reading. And if you put it in that mode, and so if you put it in absolute pressure mode, you take that pressure reading just with no tubes on, you'll consistently see an absolute temperature in inches of mercury that gives you that value. In Charlottesville, I didn't used to do this when I was really as a TAB contractor, but when I was going through a lot of research and development, it was like the first time I ever used it that way. We don't normally typically do that, but I turned it into absolute pressure mode. I took a lot of pressure readings. I kind of tend to do it once a month or so. And I consistently get a 29.3 inches of mercury for Charlottesville, which is very interesting because we're 600 feet above sea level. And if you do the general quick math, 0.6 from 29.92 is 29.32. So it's very, very accurate. It's very interesting to see that. But yeah, any of your pressure meters can probably give you an absolute pressure reading. Yeah.
Well, we have a question from Drew Winslow. It's a word problem. If I toss a baseball at you at 20 feet per second and then throw a steel ball the size of a baseball at you at the same speed, the velocity pressure you measure is much higher. Is the same true for, I'm not sure if that was meant to be pilot type sensors with air at different densities? PITOT is what was typed.
Pitot, yeah.
Pitot, thank you. So is the same true for pitot sensors with air at different densities? Does a higher density result in an increased signal?
Yeah, I think the answer is yes to that. I think I'm following it correctly, but the meters that we typically use from the common manufacturers are doing automatic compensation for us. So like I said, with barometric pressure, we don't typically know that value because we just let the meter do it. So if you do a pitot tube traverse with a DMM, you're going to get an accurate measurement if you're at 70 degrees. But if you don't have a temperature probe with it and you go to measure that velocity, the density value that the meter thinks it's at is going to be incorrect because the temperature hasn't been compensated for. Now, if you take the temperature probe and you add it to it and you do your measurements while you're tracking pressure and temperature correctly, then the displayed reading on the meter is going to be accurate. I'll say another thing about the temperature probe, because some of the manufacturers give us the ability to use temperature readings while we're doing flow hood measurements. You've got to be very careful about being accurate on your airflow measurements with a temperature probe in the flow hood. The reason being is the temperature probe doesn't usually acclimate quick enough compared to a typical tab professional going to measure airflow. If I were to measure one grill at the pace of 2 minutes per grill, I'm not going to advance very quickly in my company. That's too long of a time to measure grills. But the problem is that's what you have to do to get the right temperature acclimated to the right value to get the accurate measurement from the flow hood. So really for me, what I tend to learn to do is I don't use a temperature probe while I'm measuring airflow. I assume a standard value of 70 degrees. And then I measure all my grills in a fast pace of 5 seconds per grill. Then I do the compensation after all of those values are recorded, and I adjust them because that's the faster way of going through it than trying to get it to acclimate to the right temperature. I know that was probably more than what anyone asked for, but there you go.
That's value for money. Okay, so we have another question. Dave Fansett, would modifying the tab specifications to address the mass flow calculations methodology and BAS-related sensors assist with reducing surprises during commissioning and then through ongoing building performance optimization?
I would say yes. There's something to be said about that because, you know, like the example I gave with the 125 degree return air unit, RTU unit, when I thought I was at 10,000 CFM, if a commissioning agent came out with me and somehow went to go measure that airflow with me to verify, and the temperature was down to 55 degree discharge at the time they go to commission that, we're going to end up with very different results. Okay, so whatever's on my tab report is going to be very different from what is being commissioned and verified. And so, yeah, there can be a lot of problems in the commissioning process when it comes to verifying airflow rates because we haven't locked in a density value at the time we report volume. And that's just a moving target, unfortunately. It's a moving target. So yeah, in that case of the RTU, man, I'm going to be in a lot of trouble when a commissioning agent goes out there and measures it with me at 55 degrees. And they say, you're moving like maybe 9,000 CFM, but you're not moving 10,000 CFM. And that's what your report says. And so that becomes a serious problem. We have a problem there.
Okay. Well, that is the end of the time that we have for questions today. If you have questions, if you still have questions, go ahead and pop them in there, and we'll do our best to get those answered for you after the webinar. So I want to say thanks, Scott. Thanks for coming to share this valuable information with our members, as well as our non-members online with us today. You can explore AABC's wide range of testing and balancing references from standards to training manuals and videos. Read, take an online quiz, and score over 70% and earn credits. advertised in our extensively circulated tab journal, reaching over 25,000 test and balance professionals, contractors, architects, engineers, and more. And visit the links in the image for details. And also, my colleague just popped a link in there for the publications into the chat. Lastly, as a reminder, attendees will receive an email within 24 hours with your proof of attendance. And have a great day, everyone, and see you next time. Thanks very much.